Here we have a circuit with 7 resistors in a series parallel combination with a 90-volt supply. We're asked to find the voltage drop across that 4-ohm resistor. We're calling that R7. I've just got them numbered 1 through 7, and then various resistor values. You'll see different notation in how they label it. You might even see A, B, C, D, but here I think it's pretty clear about which resistor we're talking about, and I try to organize it and show the voltage drop and the current associated with each one. So we're trying to find this V7 on the far right. There's a lot of missing pieces, and as you'd suspect, you probably need to fill in some other things to get there. So let's just start before we get too crazy and try to really identify what V7 is. Let's figure out what we can find. Right now, if you look at any one of those resistors and even the supply, we only have one thing of the three. So we can't use Ohm's law anywhere. But we do have every resistor. And so my advice would be to find the equivalent resistance. That's going to be our first step in this circuit. So we're going to find Req. Now, it turns out this is one where I think you can do some mental math where we can kind of simplify and redraw. So I'm going to do that right here. Rather than redrawing the whole circuit, I'm going to identify that from this loop through here, we hit 2 of these resistors. 2 and 4 in series gives you a 6-ohm resistor. And now I can basically replace those 2 with one 6-ohm resistor. And hopefully you see that, well, I have one branch this way and one that way, a 6 and a 6, I can now replace them with a 3-ohm resistor. And so I've basically eliminated that whole last 3 resistors, 5, 6, and 7, and combined them all to be a 3-ohm resistor. And now let's continue looking. And now this pathway from here would go through I4, this combination, which is 3, and coming back. So we can do 3 and 9 and redraw, and 3 and 9 is 12. And hopefully see that 10 and 12 work together. They're another 12. So we have 12 in parallel with 12, and that should give us 6. So I can cross all that out and replace that all with a 6-ohm resistor. So I've taken everything to the right, R2 all the way through R7, and they all simplify to a 6-ohm resistor, which I now can add. In one loop, I go through that one. I go through my 6 combination. So 3 plus 6 gives me an equivalent resistance of 9 ohms. And so I can write that in here into my circuit. So I have a 9-ohm equivalent resistance. So again, this is one where you can do some mental math if you know some of those resistor series parallel rules. I'm going to delete out some of this so I can continue drawing on here. So we now know the equivalent resistance is 9 ohms for the entire circuit. And now we can really start to break this thing down. Ohm's law says V equals IR. And so I can calculate I total now, which is just going to be the supply over that equivalent resistance. And that's going to be 90 volts over 9 ohms. Oh, that's nice. 10 amps, a nice round number. So we have 10 amps in here as our current out of that battery. That's 10 cars per second, if you think of it that way, on a highway. So every single one of those cars has to pass through R1. So that would tell us that this current is also 10 amps, right? We're in series. And Ohm's law, V equals I times R, tells us that we should get a 30-volt drop across that first resistor. So we drop 30 volts across the first resistor, which leaves a remainder of 60 volts to go to the different pathways along our source. So let's keep going here. All right, so we have 10 amps, we have 30 volts. Let's look at our different loops now, because I think we're kind of stuck again. We get to this branch here with our current. We have 10 amps go here, some splits this way, and some of our current keeps going. And it's hard to know how much, because you got this whole mess on the right side. So this is where we actually have to look at this branch downward with R2 and R3 and think about how much total resistance we have here, right? So that branch itself is like a 12 ohm resistor, right? A 10 and a 12. And so if we had a 12 ohm resistor, right, if this branch is a total of 12 ohms, then it's going to drop the remaining voltage, right? It has to drop 60 volts, right? 30 plus 60 is equal to 90. This loop through here has to drop 90 volts. That's one of our rules. And so 60 volts has to drop across the 10 and the 2 combined. And since we know that, we can actually calculate the current. V equals I times R. So I is V over R. So 60 divided by 12 tells us that we should have 5 amps through each of these, right? Remember, they're in series, one after another, so they have to see the same current. And as a result, we can actually figure out that voltage drop. It should add to 60. Well, I times R tells us that we should have 50 volts here and 10 volts here. So it checks out. 50 and 10 is 60. In that first loop, I do 30 across the 3, 50 across the 10, and 10 more across the 2 for a total of 90 volts. I have 5 amps of current down that pathway. Well, if I started with 10 amps going into this first split, if 5 went down this way, then the other 5 has to go here. So we now know the current through R4, right? Because current has to split, and you can't lose current. If I had 10, I better have 10 coming out. 5 went one way, 5 goes the other. Ohm's law says that I should drop 45 volts here. So let's look at our next pathway here. So we get to another split, all right? Let's draw in green here. So this loop, this possible way would go through here and go through R5 and make it back to the battery. That loop will drop 90 volts. Well, that loop has R1, R4, and R5 in that loop. I drop 30 volts, another 45, that's 75 total volts. That means the remaining 15 volts has to drop right here in order to make that loop rule hold out. So 15 volts drops across V5 because that is the only other resistor in that green loop. And since V equals IR, I get a current that is 15 divided by 6. We're getting a little decimal value, no big deal. All right, 2.5. So I have 2.5 amps that go here. So I have 5 amps going this way. I have 2.5 this way, which means the other 2.5 has to go along this pathway. And since I6 and I7 are on the same line, they have to both see the same current, which is 2.5 amps. And now I can calculate those remaining voltage drops. And as we suspect, this pathway, this last loop, right, if I do that in blue, right, again, this loop should also drop 90 volts. All right, so coming all the way around this long pathway is 90 volts. I have R1 is 30, R4 is 45, and so I have 15 volts to drop between R6 and R7. So hopefully when I multiply 2 times 2.5, well, there's the 5 volts, which means 4 times 2.5 better be 10 volts. And so our answer for the voltage drop across V7 is 10 volts. And hopefully you see that all of the rules that we have between series and parallel fall into place. For any individual pathway back to the battery, you drop all 90 volts. Our first pathway, the red one, is 30 plus 50 plus 10 is 90. The green pathway, 30 plus 45 plus 15 gives you 90. And the blue pathway is 30 plus 45 plus 5 plus 10 gets you 90. We also see that the current splits. You start with 10 amps, 5 goes down the first branch, the other 5 goes the other way. That 5 splits again into 2.5 and 2.5. That 2.5 will merge back together down at the bottom to be 5 and merge back with that original 5 split to be 10 to come back to the battery. And so we see that everything matches up, a nice clean fit, and we get the values we want. We have a voltage drop across 7 of 10 volts.